Good afternoon. I'm Tabitha Thompson from NASA's Office of Communications. We're at the Kennedy Space Center in Florida to discuss important research launching this week to the International Space Station. Tomorrow at 5:55 p.m. Eastern Time, Orbital ATK will launch its fourth commercial resupply services mission to the International Space Station. Cygnus will deliver critical materials to directly support dozens of more than 250 science and research investigations that will take place during the space station's expeditions 45 and 46. Joining us today to discuss a few of those science investigations are Dr. Kurt Costello, Deputy Chief Scientist for the International Space Station Program Science Office at NASA's Johnson Space Center in Houston; Dr. Brian Mottl, Principal Investigator for the Packed Bed Reactor Experiment from NASA's Glenn Research Center in Cleveland; Ken Shields, Director of Operations and Education Outreach for the Center for the Advancement of Science in Space, or CASIS; Eleanor McCormick, who is Principal of St. Thomas More Cathedral School, which built the St. Thomas More STM-SAT-1. Next to her, Pat Coleman, a third-grade teacher at St. Thomas More Cathedral School, which built the St. Thomas More STM-SAT-1. Andrew Petro, Program Executive for the Small Spacecraft Technology Program at NASA headquarters. And finally, Talbot Jaeger, Chief Technology Officer for NovaWorks and Principal Investigator for the NanoRacks MicroSat Simple. We'll begin today by asking each of our guests to provide a brief overview and then begin questions and answers. And if you're following along on NASA's social channels, we invite you to post your questions with the Ask NASA hashtag. We'll start today with Dr. Costello.
Thank you, Tabitha. The ISS program is really excited about tomorrow's launch of CRS-4 and the Cygnus, carrying new science payloads to the space station. The space station is an unprecedented national laboratory, and as such, it offers access to the low Earth environment and special characteristics there, like microgravity and the access to the low Earth environment for spaceflight, for microsats and CubeSats, which we'll be launching. There are a lot of reasons why we want to do science in microgravity. Particularly, when we take gravity out of the equation, we expose other forces and changes in behavior that we don't get to see in a 1G field on Earth. It becomes more evident what those changes can be and how they might affect us, our lives here on Earth, and our exploration goals as we move further out into space. So we're really excited about having a whole new set of investigations to take forward.
Dr. Mottl.
Okay, thank you, Tabitha. I am the principal investigator for the Packed Bed Reactor experiment, and I work at NASA Glenn Research Center in Cleveland, Ohio. The experiment I'd like to show here will be the first to specifically study the effects of gravity on gas-liquid flow through fixed beds and more generally through porous media. Packed beds are the most common type of reactor bed used in industry and are very important in space as well. In particular, for water reclamation, air revitalization, and even wicking water up through porous media to provide nutrients to plants. The packed bed reactor will not conduct an actual reaction, but will look at many of the critical parameters needed to design and operate this type of system in space. In fact, our hope and goal is to be able to design the next generation reactor to actually take advantage of the lack of gravity, reducing the overall system mass while increasing reliability.
Thank you, Dr. Mottl. Ken?
Hi, Tabitha. Thank you. And my name is Ken Shields. I'm Director of Operations and Education for the Center for the Advancement of Science in Space, also known as CASIS. We're the managers of the International Space Station's National Laboratory. And as managers of the National Laboratory, it's really our purpose to promote and enable access to the National Lab in the environment of low Earth orbit for non-traditional or non-NASA uses. Now, basically what that means is the objective of most of our projects, really of all of our projects, is to conduct science in space for the benefit of life on Earth, as opposed to NASA's primary mission, which is conducting science in space for exploration and living in space for longer lengths of time. Broad cross-section of users of the National Lab include private sector, industry, and commercial uses spanning all sorts of applications. We've got other government agencies that are utilizing National Laboratory, students and teachers in STEM programs, and of course traditional and institutional researchers. Very broad spectrum of research that we're sponsoring on station. Includes really every science topic that you could think of, every science discipline that there is, both fundamental and applied. We utilize the internal and external capabilities of Space Station, and I'm looking forward to learning a lot about the other panelists and what they're flying on the launch tomorrow, OA-4, and certainly looking forward to sharing with everyone in the audience and out in the virtual world today what we're doing on the National Lab. So thank you.
Thank you, Ken. Eleanor?
Good afternoon. Thank you, Tabitha. My name's Eleanor McCormack, and the reason that I'm here today is to share with you. I am principal at St. Thomas More Cathedral School, an elementary school located in the Arlington Diocese up in Virginia. God willing, and weather holding, and the launch goes, STM is poised to become the first elementary school in the world to have built, tested, and launched a satellite with a lot of generous help from our community. This is a historical moment for STM and for the education field, and I'm here today to share our story of our CubeSat.
Thank you, Eleanor. Pat, could you give your perspective?
Yes, I'm Pat Coleman. I teach third grade at St. Thomas More Cathedral School, and I teach the future scientists, mathematicians, engineers, astronauts for NASA and for the surrounding businesses that support that trip, hopefully, to Mars in the future.
Thank you. Andrew?
Hi, I'm Andrew Petro. I oversee NASA's Small Spacecraft Technology program, which is part of NASA's Space Technology Organization at headquarters in Washington. Tomorrow we'll be launching one of our technology demonstration missions called NODES, composed of 2 CubeSats like this one here. It'll be launched at the space station and then later deployed into orbit. The satellites were designed by engineers at the NASA Ames Research Center. The purpose is to test out the potential for using multiple small, low-cost satellites to perform complex science missions, in this case measuring high-energy particle fields in space. Each satellite has an instrument provided by Montana State University located inside. They'll each be taking measurements simultaneously, sharing that data among them, and then either one of the two can be the relay for all of that information back to the ground. This concept could be extended to very large collections of satellites in orbit, allowing us to do missions with a large number of satellites, but only needing to communicate with one at a time. NODES is one of many small spacecraft missions that we are launching this year, and we have more in development. Our goal is to advance technology for small spacecraft, especially in the areas of communication, control, and propulsion, so that we can create new capabilities for NASA's missions in science, exploration, and space operations.
Thank you, Andrew. Talbot?
Thank you. Hello, I'm Talbot Jaeger. I'm Chief Technologist at NovaWorks. And we are so excited. Small satellites are an exciting technology in the space industry today. While small sats can provide advantages over traditional large satellites, satellites assembled from building blocks, which is what we're working with, these cells called satlets, could add to those advantages. Through funding from the Phoenix program at the DARPA, Defense Advanced Research Projects Agency, NovaWorks has developed the cellularization of satellite technology. Basically, these building blocks are satlets for assembling a fully functional satellite. That's analogous to the cells of your body forming an organism. This new cell-like structure NovaWorks has developed like an embryonic cell, and we call them HiSats, designed to be configured and aggregated as reliable and flexible satellites that can do a variety of missions. An initial set of HiSat-based experimental missions are underway, and others are planned for the near future. The first of these is called SIMPLE, a Satellite Initial Mission, Proofs and Lessons. And I believe We have a picture of the way it flies. This is how it flies out of the station. And it's supported by an amazing team from NASA who supports us with the ISS program through CASIS, supporting through safety, and ISS Ops. NanoRacks is an ISS integrator, and they're working with us with JAXA and their CABR deployment. It's a very broad team. We're really excited about all the support. But Simple consists of 8 fundamental pieces, 6 HISAT cells, cellular pieces of the puzzle, and 2 solar arrays that also assemble with it. The entire satellite will be assembled on board the ISS and then be deployed as a fully operational, newly built spacecraft. It will be another first for the space industry.
Thank you, Talbot. We'll begin questions. First, we'll start with a few questions that we collected ahead of time, and then we'll go to the people in the room. And as a reminder, if you are following along on social channels and would like to submit a question, please use the Ask NASA hashtag. First question for Dr. Costello. We recently celebrated 15 years of humans living continuously on the International Space Station. We've learned quite a bit during that time. How do the experiments going up on this mission help further prepare us for our journey to Mars?
Sure, that's a great question. Back in November, we actually celebrated 15 years of continuous human presence in low Earth orbit, which is an amazing feat all by itself. But so far, we've been living that experience 6 months at a time. We have data on what happens to the human body in microgravity over 6 months. But there are a lot of questions as we move to further out in the solar system and destinations like Mars. What's going to happen on a trip that lasts more than 6 months, maybe up to 8 to 9 months to get there and 8 to 9 months to get back? What happens to the human body in microgravity then? A lot of the human research going on right now is related to our year in space, which is Commander Scott Kelly's year-long increment and our first U.S. data point on what happens to the human body with these mechanisms that change in microgravity. Do they continue to deteriorate or do they stabilize over time? That's going to help our human research program really understand where we still have risks that we need to address for future exploration.
Thank you. Next question to Dr. Model. Thank you again for the overview of the packed bed reactor experiment. How is this particular technology important to NASA, and how do you see it being applied down the road?
Okay, as I mentioned, this is very important technology, particularly to water reclamation and air revitalization, as well as delivering nutrients to plant systems. I'd like to pull up a slide which shows a sort of a schematic of how a water reclamation cycle flows. And interestingly, in almost every one of these components, these boxes, there is at least one type of fixed packed bed reactor used. In the early pre-treatment areas, we use, for example, biological reactors. And then as we go to the post-processing, we use high-temperature catalytic reactors. There are also beds used to remove iodine and calcium for the polishing treatment.
Great. Thank you, Dr. Model. For Ken, one of the projects intended for the station through this launch is focused on flame-retardant textiles. Could you explain why that's important to us?
Yeah, sure. Tabitha, that's a great question. Milliken & Company is actually the company that is involved in this flame-retardant experiment on Space Station. The experiment is entitled BASM, and basically what Milliken is attempting to do here, what they're planning to do, is to test the propagation of flames in microgravity on flame-retardant textiles and materials. And the anticipation is that the observations in the lack of gravity and lack of convection will be different than what they observe here on Earth. And from that, they are hoping that they will be able to make improvements or enhancements to these materials and these textiles. Now, to me, what's a very unique and very tangible application of this experiment is these enhancements and improvements to these materials could actually be used to save lives. Those of first responders, electrical workers, and firefighters in general. So this is a great example, once again, of how industry and the private sector can exploit the International Space Station's National Laboratory and microgravity in general. We've got a video that we'd like to queue up right now that I think is a terrific way of explaining exactly what they're doing on Space Station.
We go around to many industries all over the country. We're in front of some of the top R&D people at the biggest companies in the world. And these folks, once they see about what they can do in microgravity, they get a ton of project ideas. Like the folks here at Millikan, they're developing a flame-retardant textile for clothing that a lot of people will wear.
We're trying to design and engineer, put on the right chemicals such that the textiles don't burn. So this is, think of, for the military, an IED. Think of a firefighter when they're going into a burning building. And it's really, again, trying to protect the person so they don't get second and third degree burns. We try to use unique insights and meaningful design and deep science to deliver a good to the world and to our customer.
So they're flame retardant textiles that they're trying to develop. Seeing what happens when they burn without gravity is very important, because gravity gets in the way of a lot of other phenomena. So when they see that, they can really understand what's going on and apply that back down to their processing on Earth.
It's really nice to have a lot of camera and digital work up there so we can look how it burns, and then we're going to get the samples back, bring them here, and then take them through a litany of analysis methods so we can find out how hot the flame was, all kinds of good nerdy stuff. I mean, ultimately, we want to deliver an innovative solution to the market. We want to protect people, and we want to have the best product out there that lasts the longest.
So this can really save lives, and that touches home to everyone. So that's why it's a great partnership to work with Millikan, because the goals of their project and the goals of our mission align very, very well.
Thank you, Ken. Eleanor, when you introduced the discussion about the students, and you do have a large contingency of students and parents here for the launch, which is pretty exciting, you talked about the kids being involved in every aspect of the design and construction of your satellite. Could you talk a little bit about how you involved the students in building STM-SAT-1?
Sure. Thank you, Tabitha. Our whole experiment in building the satellite started the day that the Discovery shuttle flew over D.C. If you could just cue up that picture, our students were able to form up the shuttle. We figured if we did this out in our parking lot, you can see our school in the background. We have our playground as our parking lot. And we figured if we did this, maybe they would see us from space. So the children were very excited. We formed up the shuttle, were able to take a picture, and it began our story. But actually, after we did this, we realized we have children that are pre-K 4 to 13 years of age. And what did they really know about space and the space exploration? So we took hold of a book called Team Moon, which was written and tells the story of how 400,000 people got the Apollo 11 to the moon. We all know of the famous and the first, but do we really know who those 400,000 people were? And we felt it was important for the children to know that many hands do make the shuttle go up. And they learned about not only the astronauts, but about the technicians, the camera people, the scientists behind the scene, and even down to the seamstress who sewed the astronaut suits, maybe with the fabric that we will see in the future, but this is what they did. And the children came to understand it takes many people. So we started with the book. We took the information from the book, and from that and many others, if we could have our next slide, we involved the students in every aspect. Here you see their students are building our antenna that will receive the images from the camera that's on the CubeSat. If our next slide could also show, the children were highly involved in the building of the antenna. Every student touched or turned a screw or in some way put it together, took it apart, put it together, so that we would gain an understanding of what this piece was that eventually now sits on top of the school and has the receiver for the images to come through. And if we could go to our next one. You see, this is our actual CubeSat. It's a small one. It's 4 by 4 by 4, and the payload on it, you can see right there, is a cross, very indicative of our school and who we are. A medal blessed by the Pope, and the container that has some artifacts that a family was able to send up into the when we launch our cube. And there's a camera on board. Those are main components for what we have on the camera, on the cube itself. And Pat will speak towards our testing that we did.
Okay. Our CubeSat, which we called Mission Possible, the children were obviously very involved in it. One of the, if you could pull up that next slide, we had to do some aerial testing, high altitude testing of our CubeSat. We had to make sure that the camera was working. We got it up to over 800 feet. And it was very successful. As it was, the pictures were downloaded, they were clear, and we did 2 tests, high altitude tests, to make sure that everything would function. It was really important for the kids to understand that you test and retest. And in order to have a successful launch, you don't just put it together and send it up. The next slide will show we had to do a fitness test, a fit test, and we had to make sure that that cube would actually fit into the pod, the deployment container. And Connor from NanoRex came out. There were over 400 students in the auditorium. You couldn't hear a sound. They were so quiet and he was speaking very softly, telling them exactly what he was doing, why he was doing it, and it was successful. It fit, and the kids were very excited about that. From that, if you could show the next slide, we've gone on quite a few field trips. My 3rd graders went to Air and Space in Chantilly and saw the video about the next step for NASA, making sure that the astronauts can be out in space for long periods of time. In order to get to Mars, it would be over 9 months to get there, a year there, and 9 months to come back. So they're very excited about the possibility, because in 20 years they are going to be at that point where they will be the scientists and the mathematicians and the engineers that will help make that a successful project. So this slide shows us the 4th grade students at the Orbital ATK, and that's where our CubeSat is going to be packaged and put on, so that it will be launched tomorrow. And that was another preparation for them to understand that it's many hands that put all of this together. Our last slide is our signature slide, and on there we involved the whole community. All the students from pre-K to 8th grade have signed it, the faculty, the parish. We have alums have come in and signed it, and we also had community members. Anyone who was interested, was involved with the project, they were able to sign their signature, and then we compressed it down to that one little metal plate that will go up with the CubeSat.
Thank you, Pat. I think you guys have done a great job to prepare a group of students who might someday work for Andrew. Andrew, we've talked quite a bit over the past couple of days about how CubeSats are so popular, and one reason is the affordability aspect. Could you talk somewhat about why they're so affordable, or what technologies have enabled that affordability?
Yeah, there's a couple of things. One has just to do with the fact that you have a standard size and shape, and that allows you to package these to ride along with other payloads in a way that's simpler and then therefore less expensive, because it doesn't take a lot of unique engineering work to figure out how to package this with the other payloads. That's one thing. In particular, though, with this particular satellite, it's probably one of the lowest cost satellites that have been used for any kind of science or technology mission. And I'll pull out another visual aid to illustrate that. The the computer in this satellite is just a smartphone. It's a commercial off-the-shelf smartphone that's been programmed to control the satellite for its mission. And this was tested a couple of years ago with our series of PhoneSat missions, worked very well, and it's incorporated into this and a number of other satellites, CubeSat satellites that we've developed. And the investment that was made decades ago in the kind of technology that enables the consumer products that we all use now was considered a spin-off from all of that R&D work years ago. We can now turn around and use that spin-off in the products that we're developing, and now we're able to do complex science missions using that type of technology and benefit just like everybody else does on the planet.
Thank you, Andrew. And I think we're all eyeing what you have next to you, Talbot. Could you talk a little bit about this? And also, you mentioned when you did your overview that it has 8 pieces only. So
yes, the astronauts will be dealing with 8 pieces, all launched separately. 6 of those I brought in their model form. And at the risk of a live demo, I'd like to show what the astronauts will be doing. They will be one by one assembling the satellites. At the end, adding 2 solar arrays. At this step, this is a single cell of the satellite, and if I can get my orientation right, basically, we have the astronauts use a mechanism to lock in these pieces. And they do that one by one and do the same thing for the solar arrays. And then we have a fully functional satellite that, as assembled, once it's deployed from the ISS, it will understand that it has been assembled, understand its components, and fly just as a traditional satellite. So it will be a unique experience to actually assemble a satellite in orbit. This is a precursor to assembling them with robotics, to assembling larger craft than we have today, preparing for explorations out into the universe. But once we've broken down satellites into their basic fundamental cells, sort of in an embryonic cellular way, we can grow to any size, not just small. And that's where this is really going to come in handy as we go forward in space.
Thank you, Talbot. We're going to go to questions now in the room. Just a reminder, if you're following along on NASA's social channels, you can submit a question using the Ask NASA hashtag. Do we have any questions in the room for any of our panelists? Go ahead.
I want to congratulate the people from St. Thomas More School on the really remarkable work that you seem to have done. And so if we had other principals from other schools or other educators here in the room with us, and they were interested in getting started in something like this, what would you suggest that they do? How do they get started?
Well, I think as with any project, you have to really take a passion, pull that passion into whether or not this is something that you really would take hold of and build into a curriculum. It's not just a one-step idea, but you have to be willing to take risk, be willing to really come up with a plan that you believe your community would support, and really just take hold and, I guess, pull together. We started with a think tank. This is how we actually began our project. And those teachers that were interested in staying after school stayed after school, and we kind of pulled together, what do you think we could do? The flyover was wonderful. It brought such excitement to the school. You felt like you could just reach up and touch that the shuttle. And so what are we going to do with it? How do we harness that excitement? And we looked at every student being involved, much as I had spoken of when I talked of Team Moon. You have to make sure that you're reaching out to all the students. And then how do you do that within the school curriculum? So we brought our teachers along, and we took hold of the guidelines and the standards and what's asked. Like in third grade, they're to study gears and pulleys. Well, how does that fit into a project? So I think a principal or any person that was guiding the project would need to know what the requirement is that needs to be met within the school curriculum, and then how do you embed it into that everyday lesson. And it starts with an idea of one project. What's your project going to be? We chose the CubeSat because NASA does have a program that involves schools in CubeSats, and it was available. We're so lucky to be in Washington, D.C. We have all of the museums. We have such a community willing to support us, and that's how we chose the CubeSat. But you could do that with whatever your passion is. Maybe they have other community resources available. So I would suggest you look around and see who's out there to help you, and really know your guidelines and know where you're going down the road. It starts with a great lesson plan and taking that plan forward. But you have to have that little core of STEM people that will stick along with you. So that's what I would recommend.
Just as a follow-up, so at what point did you get somebody like NanoRacks or CubeSat or whatever? Where do they come in? At what point?
Well, once we knew what we wanted to do, that we would try to build a satellite. Of course, I'm admiring the others down the road here. And we did try that same antenna display, so we didn't make that work, but we found another way. So you look out and see what the community has. So we selected the CubeSat, and we went online. We Googled it. What would a CubeSat be? What would be the advantages to teaching about it? How would it inspire the students? What's its use? What would you do with it after the fact? Where would you go with it? So we chose CubeSat because it was doable, affordable. We're a Catholic school with limited budget. So we went ahead and just developed from there all of the pieces that built the cube. So you have testing that you have to pay for. You saw the high altitude test. We were fortunate that the company who came to perform the tests for us charged us only for the helium. So you work a few deals, and then NanoRack came into being because they were the ones that would support us, came out to see us. We have a mission operations center built into the library at the school with a countdown clock that's ticking. And NanoRacks came out and kind of gave the children different lessons of what would be done and what we could do as a school. And we just reached out to the community for that support. NASA has been wonderful, obviously. One of the very first points that we started with was taking the teachers to Goddard, because we aren't scientists. We did a teacher field trip first and educate the educators and then reach out to the community.
Ken?
Hi, Ken Kramer for Northeast Astronomy Forum and Universe today. I have two questions, one for the elementary teachers. I guess you're going to be getting images back. Could you talk a little bit about what you're planning, how many you're going to get, and how will you get those images? And for Andy, I think on the InSight mission coming up, you've got 2 CubeSats going to Mars. I wonder if you could talk a little bit about that and how you've evolved from Earth orbiting now to interplanetary. Thanks.
Well, what we hope the cube will do, we have a camera on board, and the way the images should be received, with a lot of hope. We have a ham radio. We bought a ham radio, and we have slow scan TV connected, and the images once sent to us and goes to the ham radio, With the software we've installed on the computers, they should be able to produce the images that we're hoping the camera will take. We actually did do a check on images sent and received via the ham radio. And, oh, by the way, we did not know when we started this whole project you had to be licensed as a ham radio operator. So we learned a lot. And what you do when you find out on a Sunday that your high altitude test is on that Wednesday, and you're hoping that the ham radio will receive, and we found out we had to be licensed, we borrowed a community member who had his license, who we give space to use in the school, and he agreed to come and be the licensed operator. So that's how we hope to receive them. We have 2 backup systems. In case the ham radio doesn't work, we have a portable antenna. We have the antenna I described, and that should hopefully produce an image. And then we do have RMOCs, remote mission operation centers around the world, and other ham radio operators that hopefully will collect something as the camera's producing some images and send those along to us. So the students' project doesn't end with the launch, though we'll be very grateful when it does go. And it will just then evolve into lessons about cameras, pictures, what would be the reason you take them, et cetera, et cetera.
Okay, on the question, I'm glad you brought up, you're talking about the Marco CubeSats. And going back, our program has a project called ASARA, which is a JPL Aerospace Corporation project to demonstrate a high-gain antenna on a CubeSat. It uses the back of a deployable solar panel as a reflect array that works as a high-gain antenna. So they'll be demonstrating that technology on a mission that should be launching early in 2016. Others at JPL have taken that idea and applied it for the Marco CubeSats, which are 2 6U CubeSats that will fly along with the InSight mission to Mars. They'll separate from the main spacecraft that's going to land on Mars and serve as a communications relay during the descent and landing. So for us, this is a great success because it's a technology we invested in a couple of years ago. That project's coming along to demonstrate the technology, but the concept has already been applied for another mission that's not in Earth orbit. It's going all the way to Mars. So I think it's probably one of the first examples of anything like that in terms of using CubeSat-scale spacecraft on an interplanetary mission. And it's also a great success to see a technology that we invested in being so quickly applied in a real mission.
Thank you, Andrew. And I believe we have now a question from Fox News on the phone.
Hello, this is Phil Keating. Thank you very much, and I'd like to address my question to Principal McCormick. Children, as you well know, are the dreamers, and your kids have put in a whole lot of heart and soul and time and energy into this mission. Unfortunately, occasionally, as we have learned over the past year, as the past 2 U.S. commercial space companies had disasters trying to launch satellites and science experiments, for all of the scientists of all ages who have invested so much time, it's absolutely devastating. So I'm wondering how much devotion and dedication and time have your students put into this, and what are they doing to ensure this is going to be a flawless delivery to the space station?
Lots of prayers. That's what we start with. But it has been about a 3-year process. The flyover really was the point that solidified where we were going. Prior to that, we had robotic clubs built into our curriculum, and we also had a program that comes out of MIT and now is with the Navy, the Sea Perch program. So our students had a lot of time invested before the CubeSat in the robotic field and in electrical components as they built their underwater rovers. And then the CubeSats sort of solidified into 3 years. But we spoke along the way. It's a process. If the Cube never was to launch, it was a process. The learning that takes place was key. And we wanted the students to be able to see that things that are worthwhile sometimes take a long time, and it takes many people to be involved. And we did have failure to some degree with our antenna. We tried to use the tape measure, so to speak, and the children went through a lot of experimentation at what adhesive would hold, etc. And we never could get it to the point that it was approved by NASA, so we went to a different method. So the children have known some failures along the way, but we simply look at them as opportunities for growth, thinking outside the box, what other way can we do it? So I believe the children have gained a ton of information just to know that there takes many little pieces and parts to make the bigger ones work. They'll be quite fascinated to know that they can build to that. But I think they're really going to be fascinated knowing that another school entity was able to make the tape measure work. So we'll continue to explore and use some of those prior failures, so to speak, as those opportunities for where we'll go in the future.
Yeah, Tabitha, I'd like to expand on that answer, and Eleanor, that was great, and to also address Phil's question about failures and how students and educators respond. And I think that's one of the greatest lessons that our kids learn from these project-based STEM opportunities. Number one, they're learning to collaborate. They're learning the true meaning of teamwork, and they're learning about failure. They're actually learning hands-on the tangible meaning of how failure is a step towards success. On this launch, OA-4, I think it's a great opportunity. We've got OA-4 represents the return to flight of our commercial resupply missions. It also signifies and represents the return to flight of no less than 5 STEM experiments that were lost on those launch anomalies that Phil from Fox alluded to. So I can tell you from personal experience in our STEM world at the National Laboratory, we were certainly impacted by those anomalies. We had several schools that lost those payloads, and not a single one of them even hesitated for the chance to refly again. We're looking forward to reflying a lot of those missions in 2016, but tomorrow represents 5 schools coming back to flight who lost it. So that's a great example of a life lesson and something that I think these kids and even educators will carry with them for their entire life.
Thank you, Ken. We had a question from James Dean.
Hi, thanks. James Dean, Florida today. Mr. Costello, you had talked about the year-long mission and obviously the longer trips to come to Mars. I was just curious, what is the status of assigning another year-long mission? And, you know, beyond this one data point, how many more of those do you expect to collect in the coming years?
That's a good question. Of course, the science you can do with one data point is kind of limited. We were literally blessed in this occurrence to find that we had an identical twin in Mark Kelly on the ground. So that actually gives us another identical twin to compare genetic studies with. We also have the data from the Russian crew member who's participating. So we have an N of 2 already. Additional one-year studies are under review right now, and we're in negotiations with the Human Research Program and Russia to determine when and if those would happen in the future. But there is a plan to try and generate this data, particularly if we see anything coincidental come back in these first studies. Again, we have limited data up to the 1 year mark, some of that going back to the old Russian Mir missions, but they haven't used the same controls that our studies have. So we're trying to expand on that, use the same studies that we've already laid out for 6 months to see if we run into any anomalies past 6 months. It's difficult to tell with just a couple data points, but certainly if you see a big change in one area, that's an area to push forward in the future.
On that note, obviously a little ways to go for Scott and Mikhail, but does anything generally kind of stand out so far at this point as you push beyond that sort of typical 6-month increment? Anything interesting, or is it more as we might expect, like sort of the mental aspect of spending so much time there?
That's Scott's doing great, and he'll be back soon. His 1 year increment is almost up. And some of the interesting things about our human research is that most of it contains a pre and post measurement factor to it, where that data is collected before they fly and then once they return to the ground. So in order to process a lot of these investigations, you have to have both the pre and post data first. And so most of the results will come after we have that data.
Thank you. We had another question in the audience.
Yeah, hi, Bill Horowitz, CBS News. Two quick ones. One for the principal. How much did this cost you guys, and how did you raise the money? And then I have a follow-up.
We had community support. We went somewhere in the area of about $30,000 is where we are right now. We were able to ask for grants that were made available. If you really look out there for monies that follow STEM research and STEM in education, there are grants to be had, and that's what we did. We also had some community parents who came forward and supported the program as individuals. And our PTO, our parent-teacher organization, has an auction fundraiser, and some of the funding came from that area. So in the total of what we've spent, maybe around $50,000, but the monies actually come through grants and donations and had not tapped the school budget. So that was an important factor for us, but and I believe that would be available for most people.
For Talbot on the end, I'm a little trying to visualize the uses you're envisioning for this assembled satellite. In other words, how you said you can, it's expandable, obviously, but what does that mean? How big would this thing? Could you make one, or how small? I mean, I'm just curious as to. I'm not sure I understand the architecture.
So the architecture is focusing on two real aspects. The first is because it's made from a fairly simple cell, and it gets its nature from the multiplicity of those cells, you get the first advantage that we were going after, and that is a mass-producible item. The cost of this can come way down from traditional satellites. So now you can build satellites of any size at a lower cost. So the first thing we're going for is just simply cost reduction. This is a way to build at a cost level that we haven't been able to do in space, other than in CubeSats, where there's a lot of subsidy for the launch. This brings up a whole capability of more sizes. So that's step one. What would you do and how large it would get? We currently have designed it to go up to 3,000 pounds. So where the next one we're launching actually is going to be a 330-pound launch, and they just get bigger. So we've tested and analyzed very large satellites. This should be able to not only provide rapid research, just like you saw me assemble this like an astronauts would. We have high school and colleges working. We have the Navy Academy. We have Stanford, who have built some of the payloads, and they just plug them on. So it allows a lot of the next generation of engineers to rapidly do things they can't quickly do today. They can assemble it the same way you see. So that's another thing. We're looking for flexibility, speed, low cost, and going to the next size up. We're really now figuring out how to work with the small, and now we need to go to the next level and figure out how to get back the capabilities that we need in some science with aperture. Some science is still very restricted by aperture. It needs size. And And things do need to get large sometimes in space as you get farther from the Earth. So this is where we're headed. We're trying to give that capability back to the space community.
Thank you, Bill. Other questions?
Irene Klotz with Reuters. So what's going to happen to that satellite after the astronauts put it together? And is there any possibility or any plans in the future to actually deploy anything like that from the station?
So after the astronauts put this together, they will actually deploy it. They will. NanoRacks is putting together a deployment system called KABER. This will be attached to it, and it will be launched from the ISS. It currently, in its first mission here, carries 3 payloads, 3 payloads that have been attached to it. One is, as I mentioned, is a Stanford University camera called SNAPS. It's more than a camera. It's really a camcorder. It's a video recorder. It's going to record the deployment of the solar arrays. Since this is the very first time we've used this technology, we want to look at how it deploys and how it comes alive. We're also carrying a USNA, United States Naval Academy, QuickCom-1 it's called. It's an amateur payload. The students have built it as an amateur radio. And this is actually officially designated as an Oscar satellite, an orbital satellite carrying amateur radio. They call them Oscars. And that will come alive and beacon around the world. When it comes over the U.S., it will actually notify amateur radio hams and kids and STEM all around the world to contact it and use what's called an automated packet reporting system. And it will tell them where it is. It will be able to relay messages from locations that are disadvantaged in their comm. It's a wonderful student, university-based package we've applied. And it has a third payload, which is a DARPA payload, which was provided to test out a new type of radio. It's a wonderful system that changes the comms that we have in space. We currently use a very dated technology. We're in the world of the Internet. This is an Internet communication system. It actually pulls web pages down from the distributed system. So it acts as a web client and no longer as a command and telemetry system. So we have some amazing first payloads going on here that we're trying to demonstrate.
And then I also have a question for Kirk. Could you just maybe touch on some of the research programs that were most affected by this 5-month delay in having commercial cargo from flying from the U.S.?
Sure. A lot of the scientific payloads going up on the OA-4 mission are related to materials processing. So we've been waiting for new materials to process in microgravity and also new physical phenomena to look at in microgravity, like Brian's investigation, the PBRE. We're hoping to get those on orbit so we can enable that type of research. It's great research. It's the research that once we have it on orbit, we can operate it pretty much at any time because there are no issues with shelf life or having a human subject for only a small time. So those are the types of investigations we've been working through as reserve science during the time when we didn't have other scientific payloads arrive. We're starting to run low on that end because we're going through all that reserve. So this brings forward an entire new category of those payloads that we'll have on orbit ready to run at a moment's notice.
We have time for about 2 more questions. Do we have more?
Manny Cesare with the Utica Phoenix. With these satellites, I should say, do you foresee any possible applications of 3D printing technology being applied to further cost reduce?
So, absolutely, and then some. Once you can create a system that isn't always custom designed and the system engineering has to be done, and you can make a unit cell to produce, yes, then you want to apply all the technology you can at it. So the next stage would be to improve it. The next stage would be to assemble it by 3D printing. You could do 3D printing on orbit. You just keep going. It's now in a manufacturing world and not a custom design every satellite world. So yes, that's exactly where you want to go with this technology.
Out of Earth construction of these?
We've already put in proposals to do that.
We have time for one more question.
Mine was just a quick one, and I hope I didn't miss it, but approximately how many components will astronauts be putting together for that 3,000-pound one that you've been testing or modeling?
So that one actually, the 3,000 is currently a ground demo only. The next one that comes out next should be 330 pounds, 150 kilograms, roughly 160 kilograms. That will have, its pieces, I'll say about 18 pieces, 20 pieces. And that won't be assembled by astronauts. That will actually be fitted to the side of an ESPA ring and launched as a secondary on a main Falcon rocket. And again, the only difference is instead of astronauts doing it in space, they'll do it on the ground, and they'll plug it together and lock it down, and it will ride. So it works in both ways.
Okay. Thank you to everyone who joined us this afternoon for the Science and Technology discussion. Up next, we'll have the pre-launch briefing for CRS-4. Thank you.